Welcome, Duke alumni and friends, to this session of the Duke Alumni Forever Learning Institute. It's an interdisciplinary educational program organized in a set of thematic courses. I am Chris Clark, Associate Vice President for Duke Campaigns. Prior to that, I had the pleasure of working with Steve Cummer, our speaker today, for about 12 years when I worked as the Associate Dean in the Pratt School of Engineering. So today's program is Metamaterials. What are they and what do they do? This program is part of our theme, Materials Science, Designing a Better World. Joining us today, of course, is Steve Cummer. He is the William H. Younger Distinguished Professor of Engineering in the Pratt School of Engineering. And Steve has been with us since 1999, coming from Stanford, where he did his undergrad and his graduate degree, his PhD at Stanford. So welcome to the Forever Learning Institute, Steve.
Hi, Chris. Thanks very much. Delighted to be here. My thanks to everybody for joining. Just by way of reference, I do want to emphasize that this is a super high-level overview talk of the concept of metamaterials, and as the title says, what are they and what are they good for, basically. There will be no equations. It will be almost all pictures. So if you were joining hoping to learn the detailed mathematics that underpins the work I'm describing, this is not that presentation. But if you want to dive deeper into any of these topics, my Duke email is there on the title page. I think these slides will be shared, but you can always find me. And I totally invite everybody to reach out by email if you have something you'd like to ask as a follow-up. So let me go ahead and get started. And I think the right place to start is the reference point of what is a material. You can't understand metamaterials without understanding a material. Everybody knows what a material is, but to give ourselves that common reference point, a material is really just a substance, usually natural, that has certain useful intrinsic properties. Stepping through some simple examples, we've got a diamond on the left, which of course is the hardest substance that we know of, and it's used in all sorts of applications based on that useful property of how hard and scratch resistant it is. And where that property comes from is the arrangement of the individual atoms that make up diamond. A totally different material is copper there in the middle. And what makes that useful is how its electrons fit inside its structure. And some of those electrons are free to move from one atom to another. And that makes copper electrically conductive, which is why we can use it to push electric current and electric power around. Another example is glass, which is transparent at optical frequencies. And one of the things that we use it for is the fact that the speed of light in glass is a little bit different than air. And so light bends when it travels through it. And if we shape glass correctly, we can make lenses and other useful optical instruments. It's kind of a miracle, I think, how many different material properties we have in natural materials that we can access basically from Earth. But you kind of take what you're given in terms of these material properties from this material perspective. So if we broaden things a little bit and now start thinking about composite materials, materials that are made up of more than one substance to give slightly different properties, a totally mundane but in some ways amazing material is concrete, which is just a mixture of cement and gravel shown on the left. That particular mixture turns out to have really useful properties for building things. Cement by itself is hard, but a little bit brittle and prone to cracking and doesn't last very long. Gravel by itself is just a big pile of gravel and doesn't really do much. But you mix those two things together and suddenly you have a substance that is much stronger and tougher than either of the individual components that went into it. In the middle here, carbon fiber is the same kind of story. You put two things together to get more than you put into it. Carbon fiber is sort of woven fabric that's very tough, but not stiff, and so not really useful for much by itself. But if you insert resin, a hard substance, into that carbon fiber cloth, and impregnate it everywhere so that there's no air gaps in it, suddenly you have this material that is really tough and also really light. And Mother Nature also does some interesting things and sort of even kicks it up a notch. As shown on the right here, this is a butterfly wing. And if you zoom in on that, butterfly wing's most remarkable property is probably how it looks and how colorful it is. But you zoom into that, and where that color comes from is not a substance that intrinsically has that color, not just one material, but instead it's a composite of multiple materials arranged in a very specific structure, as shown in this electron micrograph on the right, zooming in very closely. And this particular arrangement of structure influences how light waves reflect off of this butterfly wing surface and gives it that color. So this is a great example of a structured material where the structure is what gives it the material property that we notice. And so the idea of metamaterials is really taking this composite material and structured material concept to the extreme, as far as we can possibly take it. If you ask researchers in the field what's the official definition of a metamaterial, you'll get a lot of different answers from people. My operating definition, at least at the moment, that I think encapsulates what metamaterials are all about, is that it is an engineered material that uses intentionally designed structure. That structure is the essential component of metamaterials to control the effective and functional properties of that material. Often it's done to control the transport and propagation of different kinds of waves through the material. That could be radio waves, light waves, acoustic waves, vibrational waves. All of those are examples of forms of energy that travel through materials in waves. And that by controlling the structure of this composite material, you can influence those wave propagation properties to a remarkable degree. And this metamaterial concept is especially valid when those properties that you get out of this structured material are very different than the properties you get out of the component materials that you use to build the metamaterial in the first place. So given that, let's just look at a few examples over the last 20 years or so of metamaterials research. I'll say a little bit about the history of how this field got going in an example in a few minutes. But these are all examples from the scientific literature, some of which are mine, some of which are from Duke colleagues, and some of which are from other researchers. But these are all examples of metamaterials in that they are these structured composites designed to do very specific things in terms of their wave transport and propagation properties. This one on the left, I will say more about. This is really an image of what amounts to the first metamaterial that really had that name was applied to, a negative refractive index metamaterial to control the propagation of radio waves in ways that had not been done before. Down here, this is a much smaller scale image. This structure that you can see here is printed on a silicon wafer, essentially, and is just a few hundred nanometers wide in terms of this very small structure. So each one of these features is like 100 times smaller than a human hair. And this is structure that's designed to influence the propagation of light, the light that we can see. This one up here is an acoustic metamaterial that is designed to influence the propagation of sound through air. You can get a little bit of insight into what this might do by looking at the actual designed structure that makes up this overall sample. What you can see is that there is a tight spiraling channel inside each one of these building blocks, which we call unit cells in metamaterials research. And that then basically controls how tight that spiral is, controls the length of the propagation path, or how much time it takes sound in order to travel through this metamaterial structure. On the left-hand side, the spirals are, and right-hand side, the spiral's not very tight, so it doesn't take very much time for sound to travel through the structure. In the middle, that spiral is very tight, and so it takes much more time for the sound wave to travel through. And what that means is a sound wave that is arriving on this sample from this direction will be bent as it travels through this sample. The sound wave will travel faster through here and slower through here and give a curve to the shape of the sound wave that comes out. And that means once you have a curve like this, that means the wave will focus. And so what this actually is a lens for sound waves. This example down here is an interesting mechanical example of a metamaterial. If you have a sheet of rubber, for example, you just hold it in your hands. Let me line myself up for the camera. And if you stretch that rubber this way, then the other direction will shrink. You expand it in one direction and it shrinks in the other. This is an engineered structure that does the exact opposite thing. If you pull it this way, it actually expands in the other direction. And if you compress it in this direction, it compresses in this direction and shrinks in all ways. And that's another example of an engineered structural property that doesn't come in very many natural materials, if any. Okay, so let me then jump in. I've got some stories to tell of metamaterials research. So let me get moving first with really what started this whole field. About 20 years ago, very late 1990s, early 2000s, which is interestingly the same time window when I joined Duke. And so this was research area that I became active in those first few years that I was at Duke. And there's kind of an interesting story about how that happened specifically. And if I have time, I'll tell it. I think it's interesting. Okay, so negative refractive index. You may remember from high school physics, for those of you who do remember that, that materials like glass have a refractive index that is different from 1, and that controls how light bends as it travels through transparent material. Natural materials have positive refractive index. That's what's in all the textbook. And a light wave traveling into a prism of positive refractive index gets bent as it travels through it along a path like this, where it comes out of that prism on the opposite side of the perpendicular line to the surface of that prism. This is what any natural material will do that's transparent. The amount of bending depends on the value of this positive refractive index, but everything does that. There's nothing that actually prevents physically the possibility of a negative refractive index. It's just such a material doesn't actually exist naturally. And so nobody gave it much thought exactly what the implications of that would be. A Russian researcher in the 60s thought about this problem and wrote a handful of papers on the topic that at the time were interesting, but then quickly forgotten because it was just an academic exercise. Nobody could build one of these materials. You can't mine it. You can't pull it out of the ground. So it's interesting, but it's just a math and physics exercise. And what my colleague at Duke, David Smith, did back when he was at UC San Diego, this was a few years before he joined Duke, was come up with the idea of how you can create building blocks out of copper on printed circuit boards that would create a material out of this structure intentionally designed that would yield a negative refractive index where the radio wave would bend in a completely unexpected way. And the experiment worked, totally convincing to many in the community, but there was a lot of stunned discussion around this paper and around this work. Some people didn't believe it was real because it was so counterintuitive and unexpected. And frankly, that discussion and debate was really good for the field of metamaterials because the work was correct. And it really forced people to sit down and think about, well, what kinds of things can you do with this engineered structure that you simply can't do with natural materials? And so the floodgates of metamaterials research opened. And I want to pivot to another topic that put metamaterials on the radar for a lot of people. The negative refractive index work was interesting, but a bit academic. And what really engaged the broader community and general public was the cloaking research and invisibility research that was tied to metamaterials that came out in the mid to late 2000s and then some in the 2010s as well. Invisibility is an interesting topic. We've all thought about it. We've all seen it in movies, more recent ones, older ones. Ideas of invisibility show up in stealth aircraft, but that's not real invisibility. Camouflage can be pretty amazing here. I don't know if you all can discern that there is, in fact, an owl here in the very center of that image that can be difficult to see. So those were great, but really we're talking about true invisibility for preventing an object from being detectable by light or radio waves, not using science fiction or magic concepts, but instead doing things real and with physics. This is a topic, invisibility, that has been thought about academically for a long time. Lord Rayleigh is one of the most famous physicists of all time, and he was even thinking about it, shown by this paper in the late 1800s. But there was really no practical path towards achieving this, no way that was physically plausible known how to do this until 2006, when this paper came out in the super high level scientific journal called Science, one of the two best that you can ever hope to publish in. Again, Duke colleague David Smith here, Dave Schurig, who was a PhD student at the time working with David. Dave Schurig is now professor at University of Utah, and Professor Sir John Pendry at Imperial College London, who was the real brains behind all of this, one of the smartest guys I've ever had the pleasure of knowing. And the idea is this: if you can, and this is not a concept linked to metamaterials, but instead linked to math. Metamaterials is how to realize this in practice. The idea was that if you can imagine distorting space or stretching it in some interesting way, like for the invisibility problem, creating a hole in space, then you can actually write down the material properties you need in order to bend light in just the right way to make a light wave interact with an object, like something shown in the animation on the right, where light wave comes in and then there is this material shell around the center that bends light in just the right way around it and then fills in the shadow region so that the light leaving the region where it interacted with the object looks like it interacted with nothing at all. Amazing that this solution exists. Nobody knew that for hundreds and hundreds of years, but now we know it does. The question is, how do you make this material without going into the details? It is a complicated material and not something that you can just make out of glass or any ordinary material that you can access at a hardware store, science supply store, anything like that. And in fact, without the idea of metamaterials, I think this whole concept of invisibility would not have gained the traction it did. But somewhat amazingly, the concept of metamaterials was just what was needed to actually manufacture or engineer a structure looking like this that actually delivers those material properties that you need to create this cloaking shell that can hide something from light or radio waves or electromagnetic waves. The amount of attention that this work got was amazing. This was my image, so pretty happy that that this comes from a numerical simulation that we did for a follow-up paper. But getting that above the masthead in Science Times was definitely an exciting moment in my career. And so diving a little bit more in detail to how this cloaking and metamaterial problem works, I want to illustrate this in an example that my group led about 5 years after that original cloaking work. So this was 2015 or so. The idea is we have an object that we would like to surround with some material shell, and we place that object on a reflecting surface, and we want to hide that object from interaction with sound waves, not light waves, that are coming in on that reflecting surface. The sort of distortion of space that comes along with this problem is shown here, where we sort of open up this hole and sound waves just spend their time in this wedge-shaped region. What we did is we sat down, used the theory to describe what material properties we have to have for this shell, then used metamaterial design approaches to realize a physical structure that delivered those effective properties. And that physical structure is shown here, the one we built. Here's a cutaway version just in computer design. And all this is made up of is plastic plates with very precisely sized holes and very specific thickness to those plastic plates, and aligned along very specific angles in this structure. And there's open space on the bottom where you can hide an object. This person here is my former PhD student and postdoc, Bogdan Popa, who led some of this work. Actually, the student who led this work didn't want to pose for the picture, but Bogdan was willing to. Bogdan is now a professor at University of Michigan. All of the very fine details of the structure inside this design are essential to realizing those exact effective properties for controlling sound waves. Fun fact, the first version of this that we built, there was some confusion in the design over the hole diameter versus the radius. And we built a structure where this hole in the center of these perforated plates was 2 times bigger than it was supposed to have been, and made some experimental measurements that totally failed. And we spent about 3 weeks questioning everything about what we'd done and wondering whether we'd missed something essential to this metamaterial design process, when we finally realized, oh, we just need to make the holes 2 times smaller. And when we did that and assembled this structure, amazingly, it worked. This is, I'm going to pause this a couple times, but this is a movie that we assembled from experimental measurements of a sound pulse being emitted by a speaker and traveling down through a region that we sample by using a microphone that we scan from one point to another and assemble into a movie like this. This sound wave is reflecting off of a flat surface that is down here. The sound wave, let's focus on the left side here. Sound wave exits, reflects off the flat surface, and comes bouncing back up. So this just looks like a wave reflecting off of a flat surface, like you would see ripples on the surface of a pond. It's a nice expanding spherical wave that you see when there's nothing on the surface. And that's the case we have on the left panel. The middle panel is exactly the same experiment, where we have a solid pyramid-shaped object on the surface, the flat surface of the ground. And you can see that the sound pulse that is reflected from this object is completely different than the sound pulse we see from a flat surface. Because we have these angled surfaces and we have this sharp point, the sharp point prevents sound from being reflected this way, and these angled surfaces direct the sound the other way. When we then place that fabricated cloaking shell that I showed in the previous plot on top of this solid pyramid, so now we have an even more complicated object over here. In fact, this reflected sound pulse looks almost exactly like we saw for the case where there was no object at all, and dramatically different from the case where we had a solid reflecting object. So by putting this metamaterial shell over this reflecting object, we have effectively cloaked from acoustic scattering that object. There are interesting things that you can do with this. When you're hiding objects from sound, something that comes immediately to mind is sonar and underwater. And yes, I have talked to people about that sort of thing, given some guidance on how one might do it, but then I hear very little from the folks who are actually implementing this, I think, because it becomes very sensitive very quickly. One more quick design example that's also relatively current is trying to make flat lenses out of metamaterials. Normal lenses that are in cell phone cameras, in commercial cameras, microscopes, they're all made out of glass, where we're exploiting the material properties of glass to focus light. And it requires a shape that is very specific, and you have to grind the glass to be exactly the right shape to be able to focus things as well as possible. And that makes lenses relatively expensive, relatively big, relatively heavy, because they're large objects out of heavy glass. If you could engineer a material to have the properties you want, couldn't you just take this whole lens and squeeze it into something very thin and very flat and do the same job that glass does by controlling everything? And the answer is maybe, to some degree. This is work that is being pioneered by a researcher at Harvard and some of his former students. To give you a sense of what this looks like, here's a zoom in on a fabricated flat lens that is designed using metamaterial concepts. The lens itself is about 1 millimeter wide. This is a zoom in on very small spatial scales to give you an idea of what that designed structure actually looks like. I think the takeaway here, if you can see that well, is that that structure is complicated, and every point is a little bit different from every other point. And this is just a classic example of metamaterial design, where this is the structure that you are controlling in order to make this lens bend a light wave so that it focuses itself after having traveled through this lens. There are some challenges to replacing conventional glass lenses with something like this, and I'll say a little bit more about that in my final few slides. But this is a really interesting application that I think is going to find use in certain specialized optical devices. And obviously, this lens, which is extremely thin and much, much lighter than a glass lens, has a lot of significant advantages thanks to metamaterial concepts being deployed here. Oh, yes. And one last very current example of applied acoustic metamaterial concepts. This is work from my group that was published just in the last year. Did you know that you can levitate objects with sound waves? Sound waves actually can exert very small forces on very light objects in air. In water, it's actually easier to make sound waves like ultrasound exert forces on objects. And that's the basis for a whole field called acoustofluidics, or acoustic tweezers, where one uses, often for biomedical applications, ultrasound to push around small particles in water without having to contact them in order to put cells next to each other, to sort cells. And Duke has a real pioneer in this space in mechanical engineering, Tony Wong. And he and I, about 2 years ago, started this broad collaboration of, hey, can we bring metamaterial ideas to enhance the capability of acoustic tweezers to give ourselves new ways to manipulate particles by controlling those ultrasound waves? And the concept we came up with is called shadow structure. And what we're doing is we have a thin layer of water that has no boundaries in it whatsoever, compared to more conventional acoustofluidic devices that do have physical boundaries that can lead to complications with pushing particles around. In our case, the chamber is completely open, and we're using an engineered structure like a metamaterial to control the propagation of sound waves, where that structure is actually outside the water chamber, immediately adjacent to it, but outside. And this is a microscope view of one of those structures in water that we have built. There's a water layer, and the structure, which you can see, since everything is transparent, this structure you see is actually behind the water. And this water is filled with a whole bunch of small particles. And when we turn on the ultrasound in the water, what we're doing is creating a channel along which those particles will be moved and trapped. And turning on the sound, sure enough, all those particles get pushed by the acoustic wave to specific locations that are tied to that shadow structure that we put behind the waveguide. And we can do more than just that. With 2 ultrasound sources, we can actually push those agglomerated particles along this channel that really doesn't exist in the water. It only exists for the acoustic waves. due to this shadow metamaterial structure outside the waveguide. And so we're expanding at present some of these capabilities to try and develop truly practically useful concepts and devices for acoustic tweezers in collaboration with, again, Tony Wong. So some remaining challenges. There are lots in figuring out exactly how to use metamaterials for practical applications. An interesting one that I find myself thinking about a lot relates to the fabrication and design of metamaterials. You can imagine a really complicated structure being built where there's really small features and you build it over some gigantic build size. Interestingly, as amazing as 3D printing is, there are kind of practical limits to the ratio between how big an object can we build and how small a structure can we embed inside that object. And if looking in the literature, we can go through many examples of metamaterials where we look at the very smallest feature and then the overall size of the structure, and the very smallest feature inside and the overall size of that structure. And what we can build easily, that ratio is about 300, 500, something like that. So whatever the build size is, we can embed structure that's about 500 times smaller than that inside. But the reality is, if we want to make something like a real plug-and-play replacement for a lens, for example, a glass lens, out of metamaterials, we need to be able to push that ratio way farther in terms of what we can fabricate. We need structure inside that lens that is 1,000,000 times smaller than the overall size of the lens. And the same problem actually shows up in computer-based design of metamaterials. The more complicated the structure and the higher that ratio is, the smaller the internal scale is compared to the overall size, the more time consuming it is to simulate and design. But there's good news, because if there's one thing that's getting better, or two things that are getting better all the time, it's computer power and fabrication technology. Maybe we can't do this right now, but wait a year and we will be able to build and design ever more complicated metamaterial structures. So there's no question we're going to get there. Another interesting thing that is just starting to be pursued now in metamaterials research is, instead of top-down 3D printing style fabrication, how about something a little more bottom up, where we just design chemicals and mix them together in the right way, and the whole structure self-assembles into just the right thing that we need. That's often a great strategy for building very complicated structures with a lot of internal detail, if the problem can be posed correctly. In terms of what's happening in metamaterials research, I would say the first 15 years were very focused on expanding the ideas of what kind of new physics can we do? What kinds of things can we do with metamaterials that we literally couldn't do with conventional materials, without the ability to design and fabricate this specific structure? What I think is starting to happen in the last 5 years or so is the research community has started to appreciate that, well, you know what, there's just a lot of new things that we can do. It's no longer quite as surprising, the new things that you can do with metamaterials. So really, where I think things are most interesting, and where most of my Duke colleagues in metamaterials are focusing their efforts, is on applications. What can we actually do with all these new physics that is better, or totally new, better than what we could do at present, or something that we couldn't even do before? I think that the acoustic tweezers example that I just showed is a good one of that, where we're taking this metamaterials idea, which is really just a tool in the engineer's toolbox, to say, okay, let's design some structure to control sound waves that couldn't be easily done in other ways, and use that to deliver some new biomedical device technology and functionality. So that really is the end of my slides. I know this was a lot to assimilate, and I really just scratched the surface on what's happening in metamaterials, but hopefully I've given you all some idea of what they are and what they're useful for, and I would be totally delighted to answer any questions. Thanks a lot.
We actually had one in from Pete. What type of fluid dynamic computer modeling programs are used to design the complex shapes details for the metamaterials. And for the sound cloak and the reflections, are all angles of inclination similarly cloaked, or is the material solving for the cloaking of sound waves from a particular direction?
Ooh, great questions. So commercial numerical simulation software is usually enough for the metamaterial design problems. There's a whole suite of electromagnetic simulation tools and acoustic wave simulation tools and fluid dynamics tools that we use. Just a point of reference, one that we use a lot because it's easy, even though it's not necessarily the most accurate, is a software package called Composite. The second point is an excellent one, is that sound cloak, or the cloaking idea in general, does that work for just one kind of input wave, or does it work for all? Amazingly, it actually works for all possible input waves. And that's a virtue of that transformation optics and transformation acoustics design, that you're when you distort the input wave, you're distorting all possible input waves. Even though we only measured one and showed one in that movie, it works for others. And in fact, when we were publishing that paper, one of the referees of the paper insisted that we repeat the experiment with a different input wave to really prove that the structure we built would work for just more than one.
It's a question from Dr. Maccarini.
Hey, Paolo, how are you?
Yeah, how signal bandwidth influence the effectiveness of metamaterial, and do broadband designs exist?
Also a great technical question. It depends on whether you're doing this for sound waves or electromagnetic waves. For electromagnetic waves, there are challenging limits. And I think this is part of why we're not seeing cloaking devices everywhere we go now, because there's a speed limit for electromagnetic waves, and that's the speed of light in a vacuum. And we just cannot make energy go faster than that. And so if you somehow have to route energy along a longer path around an object, you are requiring that energy to travel faster than the speed of light in air if you're hiding an object from light or radio waves in air. And so there are tricks you can do to make it work for one frequency or color of light, but it doesn't work for all. In sound waves, we don't have that fundamental speed limit because sound waves are much slower than the speed of light. And so there's nothing problematic about speeding up a sound wave compared to a sound wave in air or a sound wave in water. So it actually can be done more easily and more effectively for acoustic waves in air and in water.
You know, Steve, I was listening to your presentation, and as someone who's part of the lay audience when it comes to this type of science, I'm wondering, you know, how am I going to see this science actually change the way that I live on a day-to-day basis? Is that something that's in the application future for metamaterials?
Maybe, you know, that is a tough ask to actually change day-to-day life of people. To translate those research concepts to something practical that is that practical. Something I think I have been surprised a little bit by in trying to apply some of these really interesting physical concepts and metamaterials to something practically useful is one thing to keep in mind is most practical devices are actually pretty good. Like, they are carefully designed, and it is very tough to beat them. And so where I think metamaterials in the near term are starting to appear is not really in something that you interact with directly, but a little bit under the hood. For example, David Smith has been, again, colleague in ECE and one of the pioneers of metamaterials, has been really successful in translating some of these metamaterial ideas to new concepts for very effective and very simple antennas for a variety of radio imaging approaches. For example, one of the spinout companies that came from his group's technology has developed a steerable satellite antenna that is significantly less expensive to build than most conventional approaches. And so this is the kind of antenna that would be used to communicate with a constellation of satellites that are delivering something like internet to you, where the satellites are traveling overhead constantly and the antenna has to steer its beam to remain in communication with it. You can physically steer the antenna, but that's complicated and expensive. If you can steer it electronically so the beam goes and you don't actually have to move anything, that's a lot better. And so it's kind of in areas like that where you may not notice that you're using metamaterials ideas, but they are embedded in there.
Some questions about the development for cloaking. What's the state of the art development for that? And how large of an area can we make invisible so far?
Got it. Okay. So for light, it's a challenge. One of the big challenges is this scale size that I mentioned, that you can cloak the size of the object that you're cloaking is kind of limited by the wavelength of light at this moment, because we can't build such gigantic structures. So the cloaking experiments that have been done in the scientific literature are cloaking objects that are really, really, really small to prove the concept. And the other limitation is that this is not a flexible thin shell that goes around an object. This is a rigid shell that is comparable in size to the object that you are hiding. And so that limits the practical applications in the immediate term of this kind of thing. I secretly suspect that this sort of thing is being done because it's easier to do it for static objects that don't move underwater, where you'd like to hide something from sonar, not a submarine that has to move all over the place and so you can't put a giant shell on it, but instead something that stays relatively fixed, but that you would like it not to be detectable. But again, those details are hidden from somebody like me who's not involved in that level of research. So, yeah.
So how do you interact with industries to garner support for research or translate the research to a more commercial application?
That is a great question, and an interesting one. It's harder than it looks. It's relationship building. And so it takes a lot of time. And a lot of times it can originate from either side. Sometimes a company will reach out to me and say, we know of your work and we'd like to have discussions with you about whether it can be applied to problems of our interest. Sometimes I can get lucky and ping somebody at a company who I happen to know and then find my way via connections to the right person to talk to. When things go well, as they are actually on the acoustic side, my research group has had projects in the last couple of years with Bose and Sony, both of which are sort of commercial big companies that have a focus on audio. And so we are working with those companies on prototyping ideas for how can we translate what my group knows about metamaterials and design onto specific problems of their interest that are tied to their existing devices. And it's not always that easy, because companies often have really specific ideas about where they want something to be used, and it's not always automatic to map the research that we've done onto that very specific use case. So it just takes time. You got to make the connections, and then it takes time to be able to work through some of those, that sort of design iteration to find something that can be made to work. It's fun, but it's time consuming.
Oh, yeah. What about the most promising medical application in this field right now?
That's a great question. Most promising, don't believe anything I say about what's most promising, because I am definitely not a biomedical researcher. But maybe what's most interesting, I've seen a number of ideas recently of how to use metamaterial and structured material to transmit ultrasound through interfaces that it doesn't normally transmit very easily through. And one interesting one is through the skull and get ultrasound energy into the brain. If you just put an ultrasound transducer to try and get that ultrasound energy into the brain, it's not so easy because the skull is kind of an ultrasound barrier that reflects the waves instead of letting it travel through. Metamaterials is one of those ideas where you can engineer the right structure to be able to transmit that sound wave through. And with that acoustic energy, there's brain imaging applications, brain drug delivery applications where certain chemicals can be activated by ultrasound. You can open the blood-brain barrier in order to allow chemicals locally that wouldn't normally be able to make it through. And so you gain this degree of control by that outside ultrasound. That's something that seems interesting and promising to me.
Definitely. Steve, could you touch a little bit on how our current students at Duke are benefiting from the research that's happening around metamaterials?
Sure. It's sort of all levels, the active metamaterials researchers in ECE. So that's me, David Smith, Willie Padilla, and Natasha Lichnitzer, and others as well. We all teach the basic wave and electromagnetics undergraduate course. And so one is we simply can't help from allowing some of our work to trickle into that. And so try to make some of those topics more immediately engaging to what's happening in the research field. And a good fraction of students who find themselves interested in that topic it's relatively straightforward to get them involved in research in our groups. So the level of undergrad involvement in all of this research is fairly high. Then at the grad level, in particular, the PhD level, this is a great field in how broad it is right now. And pointing just to my group, the number of different companies where my PhD students have ended up, some are in academia, but companies like NVIDIA and Apple and Intel, a lot of places have very high interest in VR, like virtual reality, augmented reality, where you'd like to control sound, or improved wireless devices where you need better antennas, and so you need electromagnetic control. These small lenses can be used in small optical devices. Just the number of areas that this work ends up touching on in future applications is really, really broad.
Awesome. One final question for you, and I wanted to give a little bit of time because I did not prep you for this question. But in your research and study with Duke, what's been the biggest aha or most exciting moment of discovery for you as you've done this work?
So, that actually has an easy answer. So it was when I was involved in that original electromagnetic cloaking work. And that was just amazing, working with some of the smartest people I've ever worked with. And it was super fun because we were way ahead of everybody else. In fact, we were working on the experiments before the original theory paper was even published, which meant that nobody was catching us, and we were just delivering result after result after result that nobody saw coming, which was great. And I started to wonder at that time whether that same cloaking concept, the underlying math, could be applied to sound waves and other kinds of waves, not just light and radio waves, which is what the original theory was. It took me way longer than I would like to admit to get to the answer that I did. The stacks of scratch paper that I went through in the time I was able to find to focus on that question, lots of that ended up in the trash. But in the end, it was in this office where I am now. I guess you can't see it because you see the background. But the day I figured out you can do this trick for sound waves, And then at that moment, like, I think I'm the only person on the planet who knows that you can do this. That was so exciting and so satisfying.
Oh my gosh, that's the best story. Thank you so much for sharing that. And Steve, thank you for sharing this wonderful broad overview of metamaterials for our audience today. It's so wonderful to have you share your knowledge with us so that we can have a better understanding of the great work that's happening at Duke.